In this video, we simulate the formation of liquid CO2 due to decompression cooling. In the numerical experiment, we used Tough2 ECO2M to simulate the upward rise of CO2 in a sand-filled long column 500 meters in length and insulated along the outer sidewall. The insulated sidewall allows decompression-related cooling to play out, leading to strongly reduced temperatures. The system is meant to investigate the processes occurring during upward leakage, including a transition from supercritical to gaseous pressure and temperature conditions. As you will see in the simulation, the decompression cooling is so strong that liquid CO2 forms. On the left-hand side of this figure, we show the initial condition by 4 color contour plots of pressure, temperature, CO2 saturation, and CO2 density. On the right-hand side is the same information plotted as a vertical profile of pressure, temperature, CO2 saturation, and CO2 density. Results will be shown in terms of the figure here, which has the same 4 vertical profile plots as shown before on the left-hand side. Now on the right-hand side is a plot of pressure on the y-axis and temperature on the x-axis and the stability fields of CO2, essentially a phase diagram. The liquid-gas phase boundary, angling upward to the right to the critical point, is shown for reference. The string of symbols represents the pressure and temperature in the column. The lower left-hand end of the string of symbols represents the top of the column, low pressure and temperature, while the upper end of the string of symbols represents the bottom of the column, high pressure and temperature. There's a lot of information in these symbols. The outline color represents the CO2 liquid or supercritical saturation. The fill color represents the CO2 gas saturation, and the line connecting the symbols represents the aqueous phase saturation. We will simulate 40 days of upward flow. Watch carefully as decompression cooling related to CO2 transitioning from supercritical to gaseous conditions leads to the formation of liquid CO2. The action starts at the bottom of the column, top of the string of symbols, as CO2 enters the column and rises upwards and cools. The progressive rise of the CO2 can be seen in the left-hand side profile plot of CO2 saturation and in the right-hand side phase diagram by the outline color indicating supercritical or liquid CO2 low in the system and then transitioning to gas. A bit later, this gaseous CO2 cools enough that it reaches the liquid-gas phase boundary, and we have 3 phases present: liquid CO2, gaseous CO2, and aqueous phase. At these points, 3-phase relative permeability is needed to simulate the upward flow. The cooling continues as the system is stuck on the phase boundary, consistent with Gibbs' phase rule, until one of the phases disappears, which does not happen here before the system reaches temperatures that are out of range of Tough2 ECO2M. The significance of this simulation is the formation of liquid CO2. This occurs because of decompression cooling. If there were a fast path leakage conduit from a storage reservoir that allowed CO2 to start leaking rapidly upward, cooling could occur, causing liquid CO2, which could potentially limit further upward runaway flow by reducing relative permeability to gas and increased viscosity of the CO2 liquid. In short, extreme decompression cooling, as simulated here, could serve as a negative feedback to accelerating upward leakage. More details and additional simulation results can be found in our Greenhouse Gases Science and Technology paper shown here. Be sure to check the supplementary material, which has links to YouTube animation results.